All right, everyone, welcome to another seminar in our ACOM seminar series, this one virtual. Today we are welcoming Aman Gupta from Stanford University, who's going to talk today about impacts of numerics on stratospheric transport. So just a little background on Aman. He did his PhD at Courant in New York with Ed Gerber, looking at stratotrope coupling and tracer transport. And I think probably a few folks in the audience are familiar with Ed and his group, but for those that aren't, the kind of work these folks do is really, I think, at the kind of fundamental interface of math and then modeling and science. So it's a really unique, I think, program. Aman also did a postdoc with Thomas Berner at Ludwig Maximilian University in Germany. So there he looked at gravity wave dynamics from a lot of different angles, and I'm really excited to see some of the work he did come out shortly. But today he's coming to you from a freshly minted position at Stanford with Aditi Shashedri, who I think a lot of you also know as well. And the work he's going to share with us, I think it has a lot of overlap with the Wacom group and the broader modeling efforts here at NCAR, especially to harmonize all of our different dynamical cores and optimize their use. So Aman, welcome and take it away.
Thanks a lot for introducing me, Nick. And thanks again for the opportunity. I'm really excited to present my work in front of ACOM scientists. So yeah, today I will be talking about the impact that the underlying numerics of a climate model can have on the simulated stratospheric transport. I would like to thank my doctoral advisor, Edwin Gerber, and my collaborators, Alan, Mariana, and Peter, who's working with whom have been valuable throughout the journey. So as the title suggests, today's talk will focus on the stratosphere. So just to remind everyone what the stratosphere is, the atmosphere can in general be divided into layers. The closest layer to the surface is troposphere, where most of the weather patterns evolve, dissipate. But the layer right above the troposphere is the stratosphere. So in the vertical, it extends from roughly 10 to 15 kilometer height all the way to 45 to 50 kilometer height, and contains almost 10% of the mass of the overall atmosphere. Now, stratosphere is most popularly known for ozone production, because tropical stratosphere is where most of the planetary ozone is produced, and where it filters all the incoming harmful shortwave radiation. Now, the figure on the right shows the vertical structure of the temperature of the atmosphere in the mid-latitudes. And what you can see here is that in the troposphere, there's a linear decrease in temperature with height. And then once we enter the stratosphere, there's almost an isothermal region above which we see an almost linear increase in height, in temperature with height. Now, this linear increase in temperature with height endows a sort of enhanced static stability in the stratosphere, because of which it is inhibitive of large-scale vertical motion as compared to the troposphere. Before understanding transport, it is important to familiarize ourselves with the large-scale circulation of the stratosphere itself, which is commonly referred to as the Brode circulation, or BDC for short. Now, if we direct our attention to the schematic on the left, the stratosphere in general can be divided into four broad regions. The first region, the tropics, is characterized by diabatic upwelling of mass from the tropical troposphere into the tropical stratosphere. And then we have the winter surf zone, where most of the planetary waves entering the stratosphere, they become unstable, they break, they dissipate, and then churn the mass all around the mid-latitudes over a large spatial scale. And then heading further polewards is the polar vortex, which is a mass of cyclonic flow, which predominantly exists over the winter pole throughout the winter season. And then to the other side is the summer hemisphere, which is usually quiescent with pretty low wave activity. But then the key thing is that the Brode circulation is wave driven. by that I mean that most of this upwelling, the tropical upwelling, which is noticed in the tropics, um, is driven through pumping of mass through the drag deposited by planetary waves in the middle to upper stratosphere, and further down. Uh, uh, this lower cell, this lower branch of the rhodopsin circulation is driven predominantly by the drag deposited by the synoptic scale waves in this region. So in this sense, all the mass that is sucked into the stratosphere is driven by the wave drag deposited in the mid latitudes at certain heights, which forces the mass to cross angular momentum surfaces and head polewards. Um, now, eh, one of the key elements of stratospheric circulation is that when we look at the distribution, the stratospheric distribution of trace gases, the distribution, the large-scale distribution, the large-scale structure of these trace gases is determined by the large-scale circulation itself instead of chemistry. So to support my argument, I would like to show this plot from Plum 2002, from the Plum 2002 paper on stratospheric transport, where so here we see two different trace gases, hydrogen fluoride and methane, and the figure shows their monthly distribution for March, monthly average distribution for March. And the interesting thing is that hydrogen fluoride has a mesospheric sink, mesospheric source, and a tropospheric sink, while methane, on the other hand, has a tropospheric source and a mesospheric sink. But despite these differences in spatial sinks and properties of these trace gases, we see very similar spatial distribution of these trace gases, in a sense that we see these layered, stacked, concave, bulging contours in the tropics, accompanied by these flatter contours in the mid latitudes, and then again an abrupt increase as we head towards the polar region. So that's very interesting, because this shows that it is the large scale movement of mass, more so than the chemical interactions of the trace gases amongst each other, that determines their spatial distributions. Now, when modeling the transport of trace gases in the stratosphere, I guess one of the predominant problems that the stratospheric community as a whole is interested in is that of ozone recovery. We still do not know. We still don't have a very confident estimate of when the ozone will recover to its pre-Montreal protocol levels. So as an example, I show this figure on the left, which was taken from Karpechko et al. 2013, and this shows this intercomparison between several chemistry climate models. And what this shows here is that once these models were constrained to have identical ozone concentrations in 1980, and they were allowed to run freely, I mean, the question that was asked was that when does this ozone concentration return? When will this concentration return to its pre-Montreal Protocol levels? And all these models gave a very different answer. I mean, there are some models that produce safe ozone levels as early as 2030. That's like 7 years from now, 7-8 years from now. But then there are also some other models that suggest projected that it will take pretty much the whole century, the end of the 21st century, 60-70 years, for the ozone to recover to its normal levels. So now what this Karpechko et al. Study did was that they employed a method called as the MDER, multiple diagnostic ensemble regression, and then they computed the correlation of this spread with many diagnostics, carefully chosen based on what processes they represent or they are most closely associated with. So they computed correlations with chlorine, which directly destroys ozone, methane, which is solely dependent on the transport and dynamics of simulated transport and dynamics of the model, and so on. And they found that the strongest correlations of this spread are with those quantities that are directly related to the way transport is handled by the dynamical core module of the transport module of the dynamical core. So what this suggests essentially is that if there's one thing we can do to reduce this spread among comprehensive models. It is to direct our attention to more fundamental sources of error, which is how the transport is handled by the dynamical core, how the dynamics are handled by the dynamical core. So basically, summing it all up in a very simple way, we see that when we are trying to assess transport in the stratosphere, the transport will be different due to differences in advective and diffusive tendencies. For instance, differences in diabatic mass flux in the models could lead to differences in transport, to differences in circulation, um, and differences in diabatic circulation, and then differences in the way the planetary waves are represented in the models and the way they break can lead to differences in transport as well. And then on the diffusion side, we see molecular and turbulent diffusion, which is not really resolved at the resolutions employed by climate models. But then, in principle, this can be another the differences in representation of this molecular turbulent diffusion process could lead to differences in transport as well. And finally, we have numerical diffusion. So any differences in the way the numerical scheme that advex tracer um, um, differences in the way that scheme is designed, or any differences in conservative properties of these schemes will directly lead to differences in transport between different models as well. So now so today I'm going to talk about transport in idealized models. So and because of that, we try to avoid as much as possible any chemistry, employing any chemistry in these models. So we directly work with the fundamental equations, the primitive equation solver of these big climate models, and we still want to focus on transport. So to do that, we employ this tracer called as the age of air. So age of air is an idealized tracer which can be very well represented using simply the dynamical core module, the dynamical core part of the climate model. And as the name suggests, age of air is it measures the amount of time that any air mass has spent away from its surface in the free atmosphere. So in our study, let's say the surface is the source of emissions of any given trace gas. Age of air quantifies how long that emission has stayed in the free atmosphere. In a sense, it's a measure of transport timescales of different chemical species in the atmosphere. Now, the great thing about age of air is that it is independent of any chemistry of the model. We don't need any chemistry to represent age of air. It can simply be computed by introducing a linear clock tracer at the boundary, which is its source, and from there it is simply advected by the transport equations, and using that clock tracer, we can compute age of air in the model over however long we want. Now, age of air does not have any spatial source or sink in the stratosphere. Because of the way we are defining it, it has source only at the surface, and it only has source in time. So if you have an air mass that is just being moved around in the stratosphere, every second it spends in the stratosphere increases its age by 1. So it only has a source in time in that sense. Now, before I dive right into the results, I would like to motivate the main reason for this study, why we started to study what we studied, by showing the age of air profile in 2 modern dynamical cores. So we took the finite volume, cube finite volume dynamical core from GFDL and the spectral element core from NCAR, and we forced them with identical diabatic forcing, and we introduced tracer definitions identically in both these models, and we allowed the tracer to advect freely over 30 years. And what I show here is the climatological age of air profile, the transport timescales we obtained in the stratosphere for these 2 modern dynamical cores. What you see here is that, in terms of the growth structure, there are some minor differences in the horizontal and vertical gradients in the age profile in color here, but then apart from that, we see that the overall profile matches is quite similar to the concentration profile we just saw for methane and hydrogen fluoride some slides back. But then it gets interesting when we compare the age at any given isentrope, say 700 Kelvin, for instance. When we do that, we notice this striking difference between the age in these 2 dynamical cores, which suggests that the transport is really off between these 2 dynamical cores, which is surprising because they were integrated at a comparable resolution. Everything was kept identical to as much extent as possible. But despite that, we see that the age in the camp spectral element core is more than around 40% higher than the age in the GFDL finite volume cube sphere finite volume core. So basically, we want to understand why are these differences? Why do these differences exist? I mean, if the differences are so fundamental, um, uh, does it really matter what parameterizations we use, how much tuning we do, how much time we spend tuning these parameterizations? If these differences are so fundamental, these will play comprehensive climate models as well, despite um, their use of advanced parameterizations. So seeing these stark differences between these two modern dynamical cores that have been prepared for future CMIP studies um, was the main goal that motivated the study. Um, so so um, so we go ahead and we design a transport benchmark test that allows us to assess these differences in transport among different dynamical cores with different numerics. And the initial motivation of this behind these tests um, was this study from Isaac Held and Max Suarez that came out in 1984, where they proposed an intercomparison test to compare the dynamics of these models of these different kind of GCMs with different numerics in the troposphere. So since a lot has changed within these almost 30 years, the model capabilities have increased manyfold, and so on. People use it for to study many different kinds of problems than they did in 1994. So we thought having a transport benchmark test is like a natural complement to their initial test of 1994. So we start with their test, and we take their idealized forcing that they propose in their study. So the Held and Suarez benchmark test for model dynamics imposes a certain kind of analytical temperature profile in the troposphere. They focus on the troposphere, so they impose a similar kind of profile centered at the equator, symmetric about the equator. They impose this kind of a profile, and then they nudge the model, they nudge the whole atmosphere towards this profile. So as a result, so using simple Newton relaxation. So when they do that, what they get is like a general circulation that resembles much of the general circulation of our planet. So the large scale dynamics are captured when you impose this kind of heating, and then you nudge the atmosphere towards this profile. Now we are interested in the stratosphere. So Held and Suarez had an isothermal stratosphere, but then we use this forcing proposed in Polvani and Kushner 2002 study, where they impose a linear a fixed lapse rate in the winter hemisphere to capture the polar vortex, the polar night. And away from the polar vortex region, the polar region, the winter polar region, they have this linearly increasing temperature, right? So basically, we took a dynamical core, we imposed these analytically prescribed forcings, and then essentially we replaced the shortwave heating with this Newtonian relaxation of the atmosphere to this profile. And then to dampen the winds near the surface, we use a simple Rayleigh damping, as in Held and Suarez. And then the gravity of dissipation near the upper boundary was replaced with the model sponge, which again dampens these fast winds towards a zero profile, towards zero. And then because we want to work in with a stratosphere which is rich in planetary wave activity, and to get a realistic surf zone like dynamics, we introduce this wave 2 topography at the boundary, centered at 45 north. And then this excites stationary waves constantly into the stratosphere, and then these waves break, and then they mix tracer around. So this is our setup. And again, we are focusing on large scale dynamics and how the transport is coupled with these large scale with the large scale dynamics. And we have eliminated any parameterizations, any comprehensive parameterizations in the model, so that we can eliminate any uncertainty associated with these parameterizations on the simulated transport. Now, again, to compute transport, we introduce a clock tracer near the surface. And then this clock tracer, defining this clock tracer or installing this clock tracer in model simply comprises of, at every model time step, we impose a mixing ratio of equal to the model time near the boundary. And then when this air with a certain mixing ratio, when this tracer with a certain mixing ratio is ejected from its source into the free atmosphere, it retains its mixing ratio. So, and then it mixes with other parcels. So at any given time, if we pick a point in the stratosphere, and then we look at the clock tracer concentration there, and then we subtract that with the present model time, that gives us the time elapsed since the parcel was in contact with its source, that is the surface. So that allows us to compute the age of air over long time scales in the model. Now, we don't have a seasonal cycle in this setup because that allows us to work with a steady state, statistically steady state circulation, and we impose this perpetual January condition in the models, and then we integrate the model for like 10,000 days in total. And the last 3,000 days, when we notice that the age has converged, the value of age of air has converged in the models, we work with that for transport analyses. We call this setup the free running test because we allow the models to run freely and evolve freely in response to the analytical forcings prescribed. Yeah. Now we consider a total of 4 different dynamical cores in the study from 2 different modeling centers, GFDL and NCAR. So we first take the GFDL pseudospectral model from GFDL, and then we take the relatively modern GFDL cube sphere finite volume dynamical core. And then from NCAR, we choose CAM finite volume, and then we choose CAM spectral element in our analyses. So broadly, in terms of how old these models are, these can be characterized as we have 2 old models, which have been, well, I shouldn't say old, but more traditional models that have been tried and tested over time. And then we have 2 new models that are still in either being prepared for comprehensive studies or have been recently prepared for comprehensive studies. And in terms of numerics, we can again divide these models into being spectral based because of the spectral convergence that they display, or finite volume based because these 2 are finite volume models just on a different grid. There are other differences as well, but yeah, that's the predominant difference. Now, quickly, the CAM finite volume model sticks to the traditional latitude longitudinal grid, and then it uses finite volume schemes in the horizontal and vertical to eject momentum and tracers both. The pseudospectral model, it breaks down everything into waves, and then it uses different spherical harmonics of different order to represent the whole dynamical field. And then the more harmonics you use, the more effective resolution of the model gets. So using pseudospectral, so this core effectively breaks everything, or it converts the whole primitive equation into a set of ODEs, which are then forwarded in time and then solved for these coefficients of spherical harmonics. Now, cube sphere finite volume uses a slightly different, slightly newer grid, in a sense that the whole sphere is projected onto 6 sides of a cube, and that allows working with a quasi uniform Cartesian grid in each of the tiles in native local coordinates. But then the schemes used again within each tile are finite volume based. And finally, the spectral element model it also uses this kind of a discretization, a cube sphere discretization, but then within each of the cell of each of the tile, it has a 3x3 or 4x4 or 5x5 spectral element, which is further used to represent which further uses a continuous Galerkin method type numerical method to solve for the weak formulation of these primitive equations. Now, finally, we are interested in testing the sensitivity of the intermodal transport differences to the grid resolution as to the vertical and horizontal resolution. So we work with 4 different set of runs. First is the control run, where I hate to call it the control, but yeah, it's the coarsest run with a horizontal resolution of 2 degrees and 40 levels in the vertical. The second set of runs is again same horizontal, but then it employs 80 levels in the vertical. On the other hand, we have the third set of runs in which we have double the horizontal resolution to 1 degree, but then we're still using 40 levels in the vertical. And finally, in the fourth set, we are doubling both the horizontal and vertical resolution. I'd like to quickly mention that, yeah, I mean, working with such broad range of resolution, especially the 1 degree 80 level runs, created a lot of data. So at some point, we were working with 60 terabytes of post-processing of data, which was being post-processed in Fortran. It took time to do this analysis. But so throughout this talk, unless specified, I would like to show the results only for these most resolved runs. But then that being said, the results are quite similar for different resolutions as well. So jumping into the results. So I hope the setup is clear by now. We have 4 different dynamical cores with different numerics and grid discretizations, and then we are prescribing identical diabatic heating profiles. We are nudging the atmosphere in these models towards identical temperature profiles, and we are installing a clock tracer near the surface that that is being advected into the free atmosphere and is being finally used to compute age of air. So once we do this, the plot on the left shows what the mean age of air looks like for the 1 degree horizontal 80 level vertical run. So this is the mean for all 4 models. And more interestingly, the color in the background, it shows the fractional age deviation, which is the standard deviation across the 4 models at this resolution divided by the mean age itself. So what we see here is that the 4 models disagree the most in the tropics, throughout the depth of the tropics, in fact, all the way from 90 hectopascal to 3 hectopascal. And many of these differences are carried over to the mid-latitudes as well, and the polar region as well, not to the summer hemisphere. So if we had a seasonal cycle, then we would see differences here as well. But then because we have a perpetual January climatology, which effectively cuts off the circulation in the summer hemisphere, we don't see these differences in model being propagated to the southern hemisphere. Now let's look at the different models and the ages that we get from them at a characteristic level. So we just use a level, say 30 hectopascal, and we look at the age in FE3. That's what we get. We see camp spectral element, which we've seen before. The age here is higher, much higher than the age in FV3. And we add the pseudospectral model, and finally we add the camp finite volume model. So what we see here is a pattern emerging. A pattern emerges in a sense that we see this dichotomous behavior between the finite volume model and the finite volume based models and the spectral based models, in the sense that these spectral models amongst themselves have very similar age profile. There's a discernible surf zone. Yeah, the age increases again in the polar region, but when we compare them with the age in the finite volume models, it's strikingly higher. And again, this is in response to identical profiles and employing comparable resolutions, comparable grid resolutions, both in the horizontal and the vertical. Why is this happening? I mean, I mean, we'd like to understand why this is happening. Like, how can the model response be so different? I mean, I'm not sure how much this matters in a comprehensive climate model, in a sense that if we had trace gas species and if their lifetime changes by 40% or so, how much would that change the dynamics of the chemical composition of the stratosphere? That I cannot say based on these idealized simulations. But then even in this idealized framework, having such drastically different age between two types of models is certainly intriguing. So we take a step back and we look at the dynamics, the resolved dynamics in these models, and we start with the GFDL cube sphere finite volume model, and we look at the zonal winds, this time at 40 levels. So we are looking at double the horizontal resolution, but the same number of vertical levels for FV3, and then spectral element and the spectral element model. So the large scale features, the tropospheric jets, are quite similar. The polar vortex structure is roughly similar. There's some differences in the model in the tropical stratosphere. Now, if I just average the winds in this region, within this red box, the zonal mean zonal winds within this red box, and I plot them for all the models here at 40 levels in the vertical, this is what we get. I mean, there's some minor differences, especially with the spectral element kind of taking its own path above 10 hectopascal. But then the situation becomes more dire when we add the results from 80 levels. Like if you take this configuration and we double the vertical resolution only, then we see that we see a regime change in the tropical stratosphere. For FV3, we have the finite volume model continues to develop tropical easterlies in the tropical stratosphere. Yeah, tropical easterlies in the stratosphere, but then the spectral element transitions to westerlies in the region. And yeah, again, the average winds shown here show this more clearly in that the spectral models, the blue pseudospectral and the green spectral element, kind of just show a drastic transition in the tropical winds. And this happens only when the vertical resolution goes from 40 to 80 levels, not when we increase the horizontal resolution from 2 degrees, which is 200 kilometer, to 1 degree. So what we see here is that we wanted to study transport differences in the model, but then what we end up with is that the dynamical cores themselves are failing the Helden-Suarez kind of test for model dynamics. So to be able to kind of do a one-to-one comparison between the models and the simulated transport in them, we first need to get a handle on the dynamics simulated in these models. Interestingly, it is the strong tropical control that emerges here that I mean, once you have, like, the tropical winds basically set off transport throughout the stratosphere. So whether, depending on whether you have an easterly or a westerly, you can have very different ages, or you have a very different transport time scale of different trace gases in the stratosphere. Now, to solve this issue, or to at least reduce the biases in the tropical winds, reduce biases or difference in the model differences in dynamics, so that we can finally focus only on the transport, we apply this nudging technique where we impose similar dynamics in the easterly in the tropical stratosphere ourselves. So this technique is inspired by these specified QB experiments in vacuum that have been done before around 2010 or so. So we borrow the easterly jet. So we borrow the easterly jet that we observe in the finite volume models, because the finite volumes and finite volume models are not that sensitive to resolution when it comes to the tropical winds. They persistently generate an easterly jet in the tropics. So we resort to finite volume models. We go back, we look at the easterly winds generated in these models, and then we create an analytical form for these winds. And then we take that form and then we impose that, and then we nudge the tropics in all the models at all the resolutions. So we basically redo everything we have done so far, but with a nudged tropics. And then we use an identical damping timescale of 40 days, which is identical to the radiative damping timescale used by Helden-Suarez and Polvani and Kushner. And we call this test the specified test because we are specifying the winds in the tropics. Now, how much does this matter? If we can reduce if we can eliminate any difference in the tropics, can we say more about transport differences among these models? Does the transport fall in place, or how does it look like? So, as a quick check, once we nudge the winds, I mean, naturally, we're able to nudge the winds to the extent that the wind difference in the tropics simply vanish. There's very small difference. So the black profile here, the black curve here is the analytical profile, and we see that most of the models stick to this profile, more so in the lower stratosphere, middle to lower stratosphere. So nudging eliminates wind differences. And further, if you look at the fractional standard deviation, again, um, between the free running test, where the models are allowed to run freely, and the specified dynamics test, we see that the color here, focusing on the color, we see that the difference among the models in age has also reduced significantly. So here we get a maximum fractional age deviation of 25%. So here we get a fractional age deviation of 8% or so. Now, just comparing the age again at a given level, the black curves here show the zonal mean zonal winds for the specified test. So once we nudge the winds, we see that the winds in the two cores, the finite volume, cube sphere finite volume core and the camp spectral element core, are almost identical. At least we get consistent easterly jets in the tropics, and the polar vortex strength is similar for the two cores as well. Now this on the right, if you compare the age at 700 at a characteristic level 700 Kelvin isentrope, if you compare the age at this level, this is how the age looked like for the free running experiments. This massive gap or massive difference between the two models, one spectral, one finite volume. And then now with the tropical easterlies nudge, we see that the difference between the in the ages between the two models has reduced significantly. I mean, yeah, I agree. There's still some differences in the model, and that's kind of what I'll discuss further. So what we see. So if I may show this plot here again for all these different resolutions at which we integrated the models, we see that in the nudged configuration under the SP, under the specified benchmark test, the models converge in a sense that the models become very quite insensitive to changes in resolution. So the orange curve shows the GFDL cube sphere finite volume core, and we see that the age of air at a level. I've chosen one level, but then the results are similar for all other levels in the stratosphere as well. That the age of air in the cube sphere finite volume model does not change much with resolution. And then if we compare the different resolution runs and the age of air in those runs for the spectral element core, we also do not see much difference there, apart from this minor difference that emerges when we double both the horizontal and the vertical resolution. So the good news here is that considering the tropical dynamics, which in part are driven by small scales, which the models have trouble resolving at the given resolution of 1 degree and so on. If we constrain those dynamics artificially, then we are able to constrain the transport differences across the stratosphere. But the bad news is that the models, they tend to start showing signs of convergence, but then they converge to different values. So these are different. So even after constraining the tropical differences in the dynamics, we still end up with different transport profiles in the which maximize in the mid latitude. The difference is maximized here, and can be we see that the age in the spectral element model is still 15 to 20% older than the FV3 model. Now we push the spectral element model further, and then we integrate it at an even higher resolution of 0.5 degrees, keeping the vertical levels to be 80. And then on the other hand, in another run, we double the vertical resolution of the camp spectral element model while keeping the resolution unchanged, horizontal resolution unchanged. And I show these in using black curves here. All we see is that, yeah, I mean, even pushing the model further in terms of resolution does not really reveal any differences. Like no major differences crop up, and we see signs of convergence in the sense that, yeah, we can now say that even at high resolutions, the age will certainly we'll obtain ages in this interval, in this given interval. Yeah. So I have not shown this here, but then we also tried nudging the winds to tropical westerlies. Um, so here I'm showing what happens when we nudge the winds to a tropical easterly profile, and we also nudge the winds to tropical westerly profile in finite volume course, and then we found that the age um, increased. Um, I mean, the age of air in the finite volume course increased unanimously for all the finite volume runs. So basically, what we're seeing here is that for a easterly run, for a stratosphere with tropical easterlies, we get a younger age. That having easterlies in the tropics significantly reduces the transport timescales in the stratosphere, while having tropical westerlies, on the other hand, increases the transport timescales of trace gases of chemical species in the stratosphere. Um, Now, we integrate the model for 27 years. So, but then these two different locking the jets in the stratosphere is kind of similar to locking the phase of the QBO in the tropics, because QBO is an oscillating signal, and then having a tropical easterly or a tropical westerly jet is kind of corresponds to different phases of the QBO, and uh, what this suggests is that during different phases of the QBO, the transport of trace gases from the tropics into the rest of the stratosphere is significantly altered because of the nature of the winds in the tropics. Um, um, so so we want to understand why that is. I mean, why does having tropical westerlies induce a higher age in the stratosphere, and why does having tropical easterlies result in a much younger age in the stratosphere? So we resort to these conceptual leaky pipe, conceptual models in the stratosphere. Like one of the models that captures the that works with age of air and how it evolves in the stratosphere is this leaky pipe model um, okay, let's go back to the stratospheric, the large scale circulation of the stratosphere. Now, in a very simplistic sense, the stratosphere can be characterized or divided into regions of diabatic upwelling and diabatic downwelling. So the tropics are mostly the region associated with diabatic upwelling, because we see diabatic ascent of mass. And then the diabatic downwelling would be the exotropics, where we see a diabatic descent of mass. Now this is now we can reduce this full transport into a simplistic model whereby we take these two regions of upwelling and downwelling, and then we average things in the horizontal in each of these regions. So what that does is that allows us to visualize the dynamics and transport of the stratosphere um, using just two columns. So uh, so so um, so the diabatic ascent in the tropics, which is shown in orange, the tropics would be the orange column here, and then the exotropics would be the blue column here. The diabatic ascent is represented using these average mass fluxes, which move tracer upwards, and then likewise in the second column associated with diabatic descent, we have the mass flux um, bringing the tracer to lower heights. And then in an average sense, the age of air average over this tropical pipe can be represented using gamma u, which is just varying the age profile varying in the vertical. And then likewise, we have the downwelling age gamma d in the exotropics, average over the blue region on the left. Now the net poleward circulation from a transport perspective can be broken into two parts. First is an entrainment flux that brings in young air from the tropics into the exotropics, and then accompanying is the mixing flux, which is the wave-induced mixing flux in the mid-latitudes, which brings in older air from the exotropics to the tropics. Um, now, one advantage of this kind of characterization of the stratosphere is that once we average things in the column, so once we average, say, the age in the tropics and the exotropics, we get something, we get an average age profile, which looks something like this. I mean, so gamma u might look something like this in the vertical, and gamma d looks like has um, uh, looks something like this plot on the right. Um, now, the leaky pipe model, when formulated in an isentropic coordinate, in isentropic coordinates, can allow us to break down the net aging of air in the tropical pipe. So it's gamma u. It's a gradient of, this is the vertical gradient of the tropical age with respect to the potential temperature. Is the vertical aging of age. So this leaky pipe framework allows us to break down this overall aging of an air parcel in the stratosphere into aging solely due to advection, that is the mass transport, advective upwelling in the stratosphere, in the tropics, and the aging exclusively due to the mixing processes that are originating in the mid latitudes. So so sigma is the density and m is the mass flux. So it's simply capturing the time scales that simply capturing the aging of the parcel due to the diabatic mass flux that comes from below. And this the second term right here captures the mixing, um, the aging of the air because of the mixing between the two columns of the age difference, delta gamma, which is simply the difference between the exotropical and the tropical age. It's being mixed around by this mixing flux. Um, because we have our model data with us, we can sort of extract these quantities from the full 3D transport simulated in the model, and we can fit it in this 1D leaky pipe model, and compute this mixing flux, estimate this mixing flux between the mid latitudes and the tropics using as a residual term in this equation. So we can obtain gamma u through averaging. We know the density, we know the mass flux, we know the difference, age difference. The only term we don't know in this equation is the mixing flux. We can estimate that as a residual in this equation. And that's what we do. So we go back to the models, the spectral element model and the finite volume model, and we compute this quantity. Now, so we first compute this mixing flux for the free running simulations, and then we do that for the specified simulations, and we see how different these mixing fluxes are that bring older air from the exotropics and mix them with the younger air in the tropics. And when we do that, for the specified runs, for the free running simulations, this is what the tropical stratosphere looks like. We have a tropical easterly in the finite volume core. We have a tropical westerly in the spectral element core. And for that, we first compute the net poleward flux in these models, that is bringing mass from the tropics into the exotropics. And that is shown using bold curves here. And then when we compare them, we see that the net poleward flux is quite similar in the two models. But then if we break that, if we disintegrate, we break that net poleward flux into the entrainment flux and the mixing flux, we see that the mixing flux that brings in tracer from higher latitudes into the tropics, that flux is significantly higher in the spectral element core than the GFDL finite volume core. And in fact, to the extent that say at 550 Kelvin or so, around that 550 Kelvin isentropic level, the mixing flux in the finite volume core could be 1/5 of the mixing flux in CAM SE. Now, when we nudge the winds in the model in the spectral element core, and we compare the mixing flux estimated from that model with the mixing flux in the cube sphere finite volume model, we see that this updated mixing flux in dashed green here lines up very well with the mixing flux in the finite volume core. So that helps us explain why the westerlies are why tropical westerlies are lead to a significant aging of the stratosphere everywhere. The spectral element model in the configuration where it has in the free running configuration where it has tropical westerlies, the tropical westerlies here are moving, or they are shifting the critical lines associated with the Rossby wave propagation polewards. Sorry, I'm really sorry, equatorwards. And what that does is it allows the mid latitude fluxes to penetrate or percolate deeper into the tropics, as a result of which they are bringing much older air from the extropics into the tropics and then mixing them around. Now once the air mixes at a given level, it is then transported by the diabatic circulation, by the diabatic mass fluxes higher up in through the tropical pipe, and that older air now, on average older air now, is again being transported into the mid latitudes, or being pumped into the mid latitudes through wave driven pumping processes. And then basically we see multiple circuits of this older air making multiple rounds in the stratosphere, as a result aging air everywhere. So basically this aging starts at the level at which we see the westerly maximum, but then we have this older age making multiple circuits here throughout the stratosphere, making age older everywhere. Now again, because we had a perpetual January climatology, we see these differences only in the winter hemisphere. But then were we to include a seasonal cycle here, we would notice that these differences are propagated into the summer hemisphere as well. That's pretty much what I have here. But then what this analysis allows us to conclude is that there still exists fundamental differences in the way models with different numerics simulate the dynamics, and then that dynamic transport coupling leads to differences in transport in different models. Now this is an idealized study in an idealized framework, but from a comprehensive modeling point of view, it's possible that the tropical dynamics are different because the wave spectrum associated with smaller scale waves is different. But then if that spectrum generated by the dynamical core is different at its given resolution, then the parameterization, say a gravity wave parameterization, is tuned to get the tropical climatology right. The parameters that we get as a result of the tuning process will be different among the models as well, as a result of which the tuned parameterization will generate a different spectrum of gravity waves in the comprehensive climate context as well. So to reduce important differences in transport, we still need to take care of these more fundamental differences at the dynamical core level. And with that, I'd like to conclude my talk. But I can summarize whatever I discussed into 3 key points. The first is that the underlying numerics of the dynamical core still have considerable influence over the transport and dynamics resolved by these models. We still see that 2 of the state-of-the-art models have key differences in the way they resolve the tropical dynamics in response to identical forcings. The momentum balance in the tropics can be a crucial factor when trying to decide what model you want to employ in your experiments. And then even after you constrain these tropical dynamics, we see that the age of air to which these models converge to are still different by up to 15 to 20%. And then finally, by resorting and then going back to simplistic models of stratospheric transport, we were able to understand why it is that the different phases or the different jets in the tropics, which are related to different phases of the QBO, it can be interpreted as the different phases of the QBO lead to significant differences in transport by changing the extratropical tropical interaction to the extent that it ages the air everywhere in the in the stratosphere. Thank you for listening.
Thanks, Aman. That was really interesting. I think we forget how important some of the underlying numerics are, sort of taken for granted that all of these things just work when we do a free running simulation. So I think this is a really good bit of information we can start a dialogue on. So folks, if you have questions, please enter them in the Slido dialog box below the live streaming video on the page. We'll moderate them and then pass them into our discussion here. So while we wait for that to happen, I was gonna ask you a sort of initial question, kind of big picture. I know you used Held Suarez sort of setup to look at the basic dynamics in the models, but as part of our sort of development and evaluation cycles, especially when we're carrying a couple different dicores, I mean, do you think that these should feature, this or any other idealized tests should really feature in our development cycle? I mean, I guess the question is, right, there's two questions there. One, should we use Held Suarez more as a test bed, or are there other tests that we should look into?
There certainly exists many different kinds of tests that allow us to analyze transport, for instance, on small and long time scales, and also dynamics. So there's Held Suarez kind of forcing in the troposphere, and then that goes well with the Held Polanyi and Kushner forcing in the stratosphere. There have been other kinds of forcings. I think there's Held Suarez and Williamson kind of forcing. So there are different kinds of forcing that focus on something, on different aspects, on getting different aspects of the large scale circulation. So you can add a seasonal cycle, for instance, again using analytically defined functions, or you can try to change the temperature gradients in the stratosphere so as to get more realistic eddies in the tropics. So I'm not sure how these tests compare within amongst each other, but then having a certain having this kind of a test certainly helps while testing a model, because everything is analytically defined, and that allows you to kind of focus on the fundamental processes.
Thanks. Let me just see
here. Well, also sorry. I mean, if I forgot you had a two-part question. Yeah, I mean, as far as this test is considered, I mean, I would say that one downside here is that we do have to integrate the model for 27 years or 10,000 days. So that becomes a limitation in terms of computational costs, because running a model at high resolution for 27 years is not easy, although it's getting easier every year with every new cluster that is installed. But still, that's one thing that I would say that is a drawback of this test. But certainly it's special in its sense that it kind of takes into account the cumulative effect of different transport processes, heat transports in the stratosphere, and then you can analyze them as a single quantity age of air.
I don't know if we have any Slido questions just yet, but if we don't, I don't see any on the web page right now, but I'll ask another follow-up question. So this issue with the tropical wind difference where SE, well, sort of the spectral models tend toward time mean westerlies. Obviously that sort of explains some of the transport differences, and there's a consistent story there, but I don't know if I missed it or not, but Do you have any sort of idea as to why the difference is so consistent among the different formulations? I know usually we talk about SE being less diffusive than the finite volume dicores, but do you have an idea of why they tend to do that?
Um, I I don't know the answer, so to say, but then I have some ideas or uh, possible uh, uh, possible reasons as to why it may be. One is exactly what you said. The finite volume cores are thought to be more diffusive in the tropics, and then or in general, the finite volume models are thought to be more diffusive. So it's possible that as we increase the resolution, they are starting to resolve some waves that drive the tropical circulation. But then in the finite volume models, they are diffused, but then the spectral models get those waves right. I mean, there have been studies that have looked at the spectrum of these waves in the tropics in idealized models, and they have found that, yeah, the spectrum is definitely different between the finite volume and spectral models in the tropics. Uh, Most likely because of diffusion. The other possible reason um, could be that again, I wanted to try this. I wanted to test this hypothesis as a PhD student, but I wasn't able to. It could be that the spectral models are designed so as to they can conserve angular momentum well, more so than the finite volume cores. So in I know that there have been some fixers that have been introduced so as to make the finite volume models conserve angular momentum. But then I wanted to try some of these fixers and see if adding those fixers in our simulations fixes the issue. I wasn't able to try that, but that's one another reason that could be possible. Because then
Yeah,
that explains westly versus easterly. They might be losing angular momentum.
yeah, that makes sense. Yeah, it's a complicated problem. I feel like there's a sort of a chicken and egg thing with some of these things,
Yeah.
but
And
yeah, it'd
and
be good to nail that down.
And if I may, if we have time, I mean, these jets that I showed, I mean, I showed a time mean profile, but then if you look at the temporal structure of these jets, we know that the QBO descends downwards from the upper stratosphere into the lower stratosphere. But then these jets do the opposite thing. They go from the lower stratosphere to the upper stratosphere. So they're not stationary in that sense. They are also propagating, but opposite to the QBO. So it's possible that these models are starting to develop a QBO, but then because of the configuration, we have a topography which induces tropical upwelling, which might conflict with a downward propagating QBO. That could lead to the dynamics that we are seeing here.
Got it. That makes sense. Yeah. Um, okay. We have one question in the seminar chat. The Slido. So, some trace species are strongly controlled by photochemistry. Do you think age of error then is an upper bound on errors?
Huh.
I
That's a
guess
good
the idea,
question.
yeah, I guess the idea is age of error like the idealized worst case or something?
Um, yeah, it's possible. I mean, yeah, well, I mean, the age of air does take into account the effect of all these dynamical processes. Um, uh, but for trace gases, yeah, the source and sinks can be important, like the way they are represented in climate models. So, um, yeah, it's possible. I mean, I'm sorry, I'm not able to give a very robust answer, but it seems likely that yeah, it's um, yeah, I'm not totally sure if it's an upper bound. Um,
There's another question now in the chat, and it's sort of related actually. So do the FB and SE models show differences in longer lived tracers that could be compared to OBS, perhaps indicating which is a better predictor? I guess if you looked at the non sort of held Suarez stripped down, but
yeah,
I can paste that in the chat if you want, if you actually want that in detail. But basically, do the two cam dicores FB and SE show differences in actual tracers?
I don't know if I'm not aware if the spectral element core has been used in a comprehensive setting. But then we have done some tests using vacuum, which I wanted to talk about, but I was not able to because of insufficient time. I mean, if what one thing that can be done is kind of running vacuum in a nudged configuration where you have these different chemical species, and you have age of air along with it, and then you compare what the time evolution of those chemical species is and how does it compare to ours. Um, um, but I don't think I'm not sure how it would compare between different models. I mean, if there's differences at the dynamical core level, then it's possible that these differences will show up in a comprehensive setting as well. But I'm not aware if that has been done already.
So I will just add we didn't do a inter diacore comparison, but we did sort of an intra comparison of transport within a model, looking at even how we nudge, just sort of the certain choices, and that. And once you get to realistic tracers, you get to sort of cascading errors where you deliver a little more of a precursor or a given tracer to a region of photochemistry, and you can get a snowball effect. So I'm actually, maybe this talks to even the previous question, I'm not even sure that this actually is an upper bound on errors necessarily, especially if you get feedbacks between chemistry and your transport differences. But yeah, once then you add into the equation looking at realistic tracers in two different fully coupled models, there's so many things going on. I don't know how you do such a clean test. I think that's the advantage, sort of what you did here, sort of stripping down and doing held Suarez type stuff, because there's a lot of other things going on between these different models too. Like they don't all have the same parameterizations even, and how they work. So these are not straightforward questions.
I mean, yeah, I've been interested in testing this in a comprehensive setting, but I've not had an opportunity to do that so far. But it would be interesting to see how much uncertainty these parameterizations add if you just add them to this kind of a setup and just let them run. But yeah, I'm sorry, I don't have any answers in that direction right now.
I think my sense is there's a lot of folks here really interested in this stuff, and also if you need even guidance in terms of help, or you want involvement from folks, I sense that there's energy here that people would like to put into understanding this problem. Because yeah, we're sort of in the situation where we need to support multiple dynamical cores, and we also, like I said earlier, are trying to optimize like which ones we use and for what purpose, and understanding all the drawbacks and pros and cons. So I think this is like a good first sort of ground leveling stab at this problem. So yeah, I would say keep in contact, and I think maybe this is even something good to come to some of. Maybe we could have you at a group meeting or something someday and talk more about this stuff.
Sure. Yeah.
I think it would be good. Yeah. So I think that means we can wrap up and just say we will, for the viewers at home, you can thank Aman for coming today and sharing this work. This is just a reminder for everyone that we will not have a seminar next week, but we will have one the week afterward. So we will see you all in 2 weeks. Aman, if you want to just stay on for a second after the stream ends, and we can end. So thanks,
Sure.
everyone.